everyone. It's my pleasure to speak today about a topic, Computer Science 2.0, that I hope, end of the day, you will have a sense for how profound is the change that we are living through at this point in human history. But before I get going, let me give a few words of introduction. So I'm a computer scientist. I've been in research all my life, which adult life, productive work life, I'd say 45 years now. Started computing back in 1980. I've been at a bunch of the major research centers in computer science. The Xerox Palo Alto Research Center, AT&T Research, IBM Research. My work has all been in the context of AI and systems. Systems fundamentally about understanding how to do programming, how to do computing at different kinds of complexity, levels of complexity. First with constraints, natural language stuff around understanding natural language using constraints, how you can use constraints more powerfully as a programming model for all kinds of complicated tasks. Then eventually the work on X10 at IBM, which was the first petaflop computing new programming language built from the ground up to write code to run on big supercomputers with 10 to the power of 15 operations a second. So all of this is to give you background on what I've done in the past. And then most importantly, back when I was at TJ Watson in 2014, about 10 years ago, my time really flies, about 10 years ago now, I came back to AI because at that point, and some of the story I'm going to tell you shortly, with deep learning, the papers from Jeff Hinton showing that these new deep learning techniques actually make a profound difference in image understanding, those had just come out a couple of years prior to that with some of the collaborators from TJ Watson involved in it. So that, to me and some of my colleagues, was like, wow, what is going on here? Does this really work? If this works, it's going to change everything. And of course, for me, coming from my background, it was always like, vision is great. I love vision, but not really. I love natural language more. That's where the real complexity of the world lies, is in how humans, the vision, the world, it's about the physical world. It's about regularities that occur in this three-dimensional world that we inhabit. It's about building systems that can understand those regularities. But as soon as you come to language, now you've got these complex systems that we call humans in the middle, interpreting that reality and expressing it in this completely made up thing that we call natural language. So the question is whether we can, in fact, apply those techniques in this much more complicated space of natural language. And as we have now seen, particularly after the emergence of the GPT-3 model in 2020, the first time that was released to the public, in fact, these deep learning techniques work really, really well with language. And what that story I'd like to explain in a little bit. But I'm coming back to finishing my story. So that step back 10 years ago was this stuff coming out from left field. I say left field deep learning, but obviously Jeff Hinton and team, Benjio, so many other people had been working on it for 30 years. So it's an overnight success that was at least 30 years in the making. So this stuff coming from left field, it's going to sort of render irrelevant the work that we are currently doing, a lot of the work that we're currently doing in research, in computer science research. So for me, that was the motivation to try to figure out what the heck is really going on. And I had the privilege while I was at TJ Watson to come back into AI research, lead up some of the natural language work there as chief scientist for deep compliance in finance. And that was very clear. You're going to have to apply the stuff. Finance, medicine are the two big places where there's major impact to be had from these new techniques. And finance made a lot of sense to be involved in. I was started out with that at TJ Watson. And then it also became clear that, in fact, if you want to work in this space, you need the data. And the data is not going to be with vendors, finance data. It's going to be with the banks. So I went to Goldman Sachs in 2017, started up the AI research lab there. And I'd say again, my team had the privilege of producing probably the first model, first application on Wall Street that deployed large language models. This was back in 2021. Maybe 2022, actually. It's already getting a bit hazy, when we used a T5 model to actually show off the shelf. We take this model down from the internet, apply it to the extraction of terms in mortgage documents. Raw documents, no pre-processing whatsoever. Model, no change whatsoever, no training. Apply that to extract things like what's the principal, what's the interest, is it a fixed interest, is it an adjustable interest, all of that, simply by asking the right questions. And that's how this whole new world, that's what this is about. After that, I've had the opportunity, now I'm at Fidelity, and I'd say at one of the most, for me at least, exciting jobs in the world, which is that you've got all of this powerful technology. And now you wish to make models that actually understand the financial world, and that can be used for all sorts of things, analyzing the current fundamental research for particular tickers, analyzing whether that's consistent or not. What are the main themes? Actually coming up with newer analyses for new tickers, new enterprises that people may not have allocated enough resource to. So in other words, building a model, a set of models perhaps, that actually are able to make sense of the economic world. That's roughly speaking my job as head of Gen AI in asset management in Fidelity. And the big deal going for us, of course, is the fact that all of these models are enormously data hungry. They need data. Where the heck are you going to get data from? AI has had this vision going back to Doug Linat in the 1980s that we will build models of the real world. And how will we do that? We will get a whole, Doug Linat's view, get a whole bunch of graduate students to write down, stuff in logic. This was the psych system. And that is how we will get our access to the knowledge, is through humans sitting down with our system and typing stuff in. Well, of course, there's a far more powerful story close at hand now, which is that, guess what? People have been writing things about the real world from the viewpoint of understanding how it works and predicting how it works in finance for a long time. These people are called fundamental analysts, and we've got portfolio managers who take the representation that these analysts are making of complex financial situations in the world, representations in text. And you've got portfolio managers taking that as input to decide how they're going to invest scarce resource, i.e. money, with a viewpoint of actually making money. So you've got all sorts of closed feedback loops within a context where there's a massive amount of text. Not just text, but text plus numbers, text plus maps, projections, things like that available to you. And at Fidelity, it's a very large number. We're talking far more than hundreds of thousands of documents available as what we have done. I say we, I mean Fidelity has done over decades in capturing this sort of fundamental analysis. So my job is to try and make sense of all of this and see what kinds of tools we can build. So today what I'm going to be talking about is two parts. The first part is what's actually happened. What is going on right now? Because it is completely different from anything you might have seen before in terms of a revolution in computing. Computing itself is the most powerful tool we have ever had for reshaping the world around us. And then even within computing, now we've got something that renders a lot of the stuff that has gone on before obsolete. How do we make sense of this? I'd like to tell you my story, my accounting of how you make sense of it. That's the first part. And then the second part, and in some sense the big takeaway from my presentation today is simply this. The real laws of the world still don't change, even though technology becomes very, very exciting. And the law of the world is when there's new technology here, it is going to take time for us to understand it and to apply it. We are in the infancy. We are in the research and development stage of deep learning, of generative AI, of large language models. Unfortunately, this stuff is so widely applicable that there is a gold rush of thousands of people, companies, getting into this from an application point of view. And I am working on applications myself. So it's not as if I'm not part of that. But we've got to understand we don't even know the basics of this technology. And as we are looking to build applications that go into production, there are going to be, and there are, innumerable pitfalls. And I'm hoping to elucidate some of these pitfalls through, illustrated with some of the work that we have been doing. So that's my goal. First, talk about Gen AI and how we got to where we are. And then, it's fantastic that it is applicable to so many different things, but there are big challenges in taking stuff into production. So if you or your colleagues are looking at deploying stuff in production, I hope there are a few things that we can, that you will learn from today's presentation. Okay, so here is and some of these slides were developed in collaboration with a colleague of mine, Nico Vasiloglu from Relational AI. We presented last year at the Knowledge Graph conference, and that was, I should have explained what the heck is that elephant doing. That's the elephant in the room, knowledge graphs plus deep learning. How do you combine these two? It's a big issue because at some sense, large language models, all about text, you're able to get so much done with plain text. Is there still a role for knowledge graphs, for actually getting a symbolic representation of the knowledge implicit in the text at a level which is much more representative of abstract concepts that might not be present in text? So that's sort of the whole sub-theme underlying this. Again, from an AI point of view, what I would say is to further locate my biases and background. Most of what you're going to see here comes out of machine learning, but there's a prior AI generation that was all built on logic-based modeling. I come from that logic-based modeling school, and now we are deploying all of this stuff. So for us, things like semantics, things like representation in human understandable fashions, things like representation, reasoning, those are absolutely critical. Okay, so what has happened? So here's my way of explaining what has happened. So we have had, going back to the 50s, we've had a notion of computation built from some utterly simple basic building blocks. Things like, well, ultimately transistors, but things that one can conceptualize as, hey, I got this little pigeonhole, I'm going to put a number in here. I'm going to move that over here, I'm going to do various operations on it. I'm going to put the number back. Things that are so trivial almost, but the big value is that billions of these can be done in 1 second. Billions of these operations can be done in 1 second, reliably. They will always do, more or less, exactly what you tell them, barring some radiation effects and stuff like this. It's on top of this utterly mundane infrastructure that the world that you see around you has been built around computation, developed and deployed in this mechanism. Now, the problem is, how do you go from something that does these kinds of billions of stupid, simple operations to stuff such as I'm displaying this stuff to you using a computer? There's a huge amounts of code running. That code was written by humans. How do they write that code? That whole framework is about humans go understand the problem that you want to solve in the world, figure out what are the representations in the computer that you need to have in order to faithfully mimic that situation, however complex it might be. And then you write the code, the algorithms to manipulate those representations, ultimately get into the result that you want folks to take advantage of. That's how we used to do it. That's computer science 1.0. And now what has happened is, using that machinery, that underlying machinery, what we have available to us is actually a new family of computers. They are still instructable. The old ones were instructable. We could tell that system what to do. So are the new ones. But they are actually instructable in what I'll call language. I have to, unfortunately, in this field, we are sort of losing a few words, so I'm going to have to reuse a word, language, which we all think we understand, in a little bit more precise and a more general way. By language, I mean anything that humans use to communicate with other humans or with computers. So I'm going to throw computers in because, of course, we're going to put code in the middle. So language includes text, tables, documents, data, code, images, audio, video, pictures, everything. The fundamental regularity underlying this is sequenced media. That's what this new technology, these new computers are able to deal with in a very, very powerful way. So we now have these. We have computers now that we can instruct using language, and they have accessible to them all the information that we might have accessible to us as professionals. Again, going back to my situation as an analyst, as a financial analyst, I'm consuming huge amount of information about the real world in the form of news, in the form of analyses that others have done in the past or now, and I'm making sense of it, and then I write out my analyses for others to consume. I am a sense-making professional in the world. There are lots of other white-collar, knowledge-based work that looks just like that. Now, for the first time, we have the potential for taking computation right in the middle of that sense-making loop, both ingesting information and producing information for others to consume. So tools that actually, if you've got computers here, we've got humans here, that look a little bit like some stuff in the middle, because like computers, they have the ability to use vast amounts of computation per second, which at some level, humans are much slower in terms of computing than the machines that we are working with. Like humans, so like computers, you got scale, and you've got this ability to access massive amounts of information instantly. Humans don't. Like computers, you have the ability to scale out your computation, but like humans, these systems have the ability to work with language somewhat in a way that humans do. And of course, that's the whole conundrum. Is it really like humans do, or is it different? And that's what we're going to explore now. So back to the 1.0, I've already described this in some sense to you, the high, big, abstract points here. You got humans generating code, humans making representations of the real world, figuring out what these are, figuring out the algorithms, writing the code in Java, Python, Lisp, so on. We've got a whole, decades of work going into designing languages. I put my language up there as well, X10, and issues about, is this code correct or not? How do you test it? How do you develop code in a robust way so that it actually does what you expect it to do in the real world as the data coming in might change? Those are the things that we dealt with in software methodology in 1.0. And the basic point there is that you basically have to know what you are doing before you start writing code. You have to know what the representations are, what the algorithms are, and then you write your code. Well, and the big issue is, what do you do when you don't know how to write that code? Don't have the representations, don't have the algorithms. By that, what I mean is you don't know how to write that stepwise procedure which will solve the problem that you are interested in solving. And that problem, give you a very simple example which led off this whole recent explosion, 2012 onwards, is labeling an image. You have images like this. And you want the piece of code that has to be written to be able to label that. That's people. That's a child, maybe a child with another adult. This is a house. That's a study. What are we doing? We've got all sorts of concepts expressed in human language with the full plasticity of human language, full power of human language. And we are expecting to write a piece of code that will take as input this image and output one of those things. Well, yes, that's what's been done. So how was that done? The basic point is you may not know how to write the code, but let us assume you have this ability to actually recognize the result, or in other words, to label the stuff. So let us assume someone here, it was Fei-Fei Li and team, go off and get 60,000 images, and they label those images. This is people, this is children, so on and so forth. Now the question becomes, is there a general algorithm where, given just this data about the real world, the raw data and the label, give that as input, and what you get out is the code for an agent that will now be given new input, may have never been seen before, and generate a label that those humans looking at the earlier labeling task would say, that's reasonable. Okay? So imagine how complicated suddenly the world has become. We are now dealing directly in ways in which the world and situations in the world are represented. I'm not doing any more an understanding of what are the data structures that are needed inside this. What are the algorithms that I need to write? I am working on the basis of actually a single algorithm. I'll mention that in a minute, stochastic gradient descent, working on essentially a uniform notion of representation. We'll come to that, deep neural networks. And you turn that handle, all you're providing as input is labeled data to a scheme like this. That's the world that we are in. There's a bunch of technical comments. My slides will be available, and there are links to things. Ultimately, what it ends up, and I'd heartily recommend this if you're trying to get a sense for what really happened here, the PNAS article by Terry Myasnioski et al. On the unreasonable effectiveness of deep learning in AI, and so on. So I'm going to jump here and get to a little bit of an intuition of why this is working. So the core idea was what I showed you before, function approximation. We are going to be working in a setting where this piece of code is computing a function from input to output. We don't know the precise function. We're going to operate in a setting where that function is figured out by code. It's not going to be exactly what we want. It's going to be an approximate function. But if it is good enough, that approximation will have to work for us. So we are going to be working in the context of function approximation. And further, we are going to take advantage of the work that was done by Hinton, Bengio, LeCun, and so on, saying that, hey, so first of all, let me just describe what that could look like. What that could look like is actually something utterly simple. Looks like these simple elements that we'll call neurons right now. They're not related to human neurons, but doesn't matter. They take input from other such things. They combine them in some way, linear way, like summation with some weights. And then they apply what is called a nonlinearity. This is an example of a nonlinearity, which sort of gives you a 0 till this level, and then gives you a straight slope. It's nonlinear because there isn't a smooth way. This is the smooth way of describing it, which of course breaks down when you are close to this point. So that nonlinearity turns out semantically to be a very critical part of how these things work. So you've got essentially a bunch of compute elements that are doing utterly simple combinations of multiplications and additions to compute the output, and then they're going to apply some nonlinearity, and then the idea is you build layer upon layer upon layer of these things. What is going on? Well, here's what you're going to do. We're going to feed a representation of our data in from the bottom. It'll come out at the top as what is the answer that this computing function, this approximation produces. We get that answer. We have our labels. We take those labels. We take this answer. We compute. Is this the same? Is it different? Again, there are representations of all of this in sort of mathematical spaces that are really critical to make this work as abstract vectors. But at the qualitative level I'm describing, there is the result produced by this system, and then there is the actual result expected. You take the difference, it's called a loss, and now comes the magic. You push that loss down through the network. What are you doing? You're going to perturb these weights that I just spoke about ever so slightly in the direction that will make it easier that the next time that input or an input like that comes in, you will get an output that is closer to the desired output. So we have a universal mechanism here for computing function approximations by really just training on data. This is what is going on in this new world. And in this data, the big deal here is that this stuff, and the gradient descent is an algorithm. If you want to get an intuition for how gradient descent works, just think of it like this. There are potentially billions of weights in here that together are computing the result that you're going to get. Think of it like this. If one of those billions of weights is actually responsible for this output, and you tweak it slightly, increase it or decrease it, will the output come closer to your desired answer or not? That's called a partial derivative. So you're computing those partial derivatives simultaneously on all of those weights, and then you tweak them in a very tiny direction according to the loss that is coming in. Conceptually, that's all there is to it. Okay? Big deal is you are doing this again, what I said before, billions of times. You're doing it on massive amounts of data, and you're doing this repeatedly. The kinds of large language models we are working with today, again, things have not been publicly disclosed, but there's general belief that GPT-4 is of the order of maybe a trillion, several 100 billion parameters. So imagine trillions of tokens, trillions of words being used, trillion. Just go back and think when you go home, is there anything in your life that you can relate to that there are a trillion of? Okay. Yeah, cells in your human body, but you don't relate to them, do you? So, right, trillions of things, these numbers are absolutely mind-boggling. So what we have now at hand is a computational mechanism that scales. The same algorithm, the same ideas of representation work from 10 neurons out to a trillion neurons. Same thing. And this is why you see in the world convergence on, NVIDIA is about to announce, I think this afternoon, what its earnings are, and the whole world is waiting with bated breath and doing all sorts of trades on this, because what has happened is all of the stuff that we are doing now funnels down into, do you have the hardware that can do these things efficiently? And so, that's one example of a company that's there. Okay, I don't have much time to go into this, but it is not just about putting these layers in blindly. It's about getting the architecture right so that, in fact, what you see, this distributed representation hypothesis, is that, first of all, the world that we operate in, even though it might look extremely complex, actually has a lot of regularity. A chair is somewhat like that. Yes, there may be an artist who'd make a very weird chair, but there are not going to be many instances of it in the world. And what you're looking for is raw data that you use to train your systems. There are going to be far more examples of chairs that look like this than chairs that don't. And what it looks like here, it's not too difficult to conceptualize. It's got a base, it's got a back, it's got some chairs. So it's a low-dimensional object. Our world is littered with these things. So the first idea is that, in fact, the real world is far from being as complex as we might believe. And those underlying regularities we can actually learn by exposing our system like this to some of that data, maybe labeled data, maybe unlabeled data even, and that was the big breakthrough. I'll come to that in a minute, how you can just use unlabeled data to get the system to actually learn representations of the real world. Now, in the vision case, what it turned out is, and this distributed representation hypothesis is that you actually want to build your neural network in a succession of layers. That's why it's called deep learning, where in fact the intuition was that things at a higher level will actually learn abstractions that are closer to the output, whereas the things at the lowest level, just closer to the input, are going to start abstracting things from the input. So here you see lines and edges that's being captured here. Now you start to see some contours. Now you actually start to see faces represented, features of faces represented at a level. This is a face detection program that we are training. So that's the sort of idea behind distributed representations is we don't have to program this. It will get learned by the system from the data made available to it. So that's an arbitrary general picture I've shown you for machine learning. Where do large language models come in? You take those ideas, you apply them to language. How do you apply them to language? First of all, there's a lot of research in this space. I'd say there may be 1,000, maybe even 10,000 active researchers working in this space, which led to this transformer architecture by a group of researchers at Google in 2017 that has turned out to be instrumental. Before this, the problem was people were working with large neural networks to work with language. But the challenge is language has a lot of complexity. Language is linear in nature, and furthermore, words that occur at the very end may have a disproportionate influence on how the word at the very beginning should be understood. The long-range dependencies. And the techniques that people had to deal with that, so-called LSTMs and RNNs, were simply not good enough. So a lot of the underlying semantics of natural language was not being captured by those techniques. We, of course, had good results. And as you move out from the old way of doing natural language processing, NLP, NLU, to the new way, there were interesting new results that we got from using LSTMs and RNNs. But the big breakthrough here was to recognize that this idea of going and how the RNNs and the LSTMs work is, roughly speaking, there's some internal state that is managed, and then you go a sequence, a token at a time. You have this internal state, you process the representation of the token, you update it, go look at the next, go a sequence at a time, all the way down the sequence. Clearly, by the time you come to the end, any influence that the first would have on the last is mediated through this single bottlenecking state. Not so good. So the idea here behind the transformer is fundamentally we're going to do this. We're going to take a sequence like this, we're going to take a sequence like this, and we're going to have all possible points between them interacting, a compute element, a neuron there, so to speak, allowing for a direct pathway of interaction. It's parallel, it takes more time, it's slower to compute, but you, from a semantic point of view, are enabling pathways that were very difficult to work with before. That was a magic bullet, so to speak here, silver bullet, that actually made a huge difference. Today, almost 90% of the work being done in large language models is being done on top of transformers. There are newer ideas now, newer architectures out, which which are also quite promising, but really the bulk of the work is still being done with transformers. And then the next big, so these are the 5 pillars to understand large language models. The next big deal is, okay, what is actually this function going to do, this little black box I've talked about that takes as input stuff and produces output? Obviously, we want it to take as input some language, the cat on the hot tin. And what we want it to do now as output is give a probability distribution over the next word. And that is called language modeling. It has been called that for a very long time. And you get these words with different probability distributions, and then you'll have some system sitting on top that looks at it, maybe selects the one with the highest probability. Oh, that's roof, the cat on the hot tin roof. You feed that back in, and you repeat this process. So you can generate lots and lots of text. Here's the amazing thing, no labels required. I start with a piece of text, and I simply chop it up into pieces. I know what the next word is. And that I can use as a label to help train this little function that I talked about. Yes, please, go ahead.
So an LLM can reflect a lot of biases we can learn from the text, right?
Totally.
How do we mitigate those biases? For example, if I read
Yes.
on internet a sentence like, a nurse took out her keys, right?
Yeah.
It will assume that all the nurses are female.
Absolutely.
How do we mitigate that?
Yes. So wonderful question, completely makes sense. Think of it like this. I'm still describing the transistors in this view of computing, and you're asking about a result at the very top. So I hope to get to it at the end. Very important problem. So maybe I will segue onto this point. So before in CS 1.0, I had this ability to programmer precisely describe what is going on. And if the result is something that doesn't work, my boss gets to fire me, because I'm responsible for it, and all of that stuff is under my control. That's no longer the case with this way of doing business. It's all about the labels. And as I said, I as a programmer don't even specify the algorithm. We know what that algorithm is. It's gradient descent. We use that. We know what the structure is. So I don't have any agency, any influence on deciding all those things. The only agency left is in the data. But now what the system learns from this data is going to be approximate, and it may be very different from what you thought it should learn. And now we have to deal with all that. So that in the new way of doing business, you lose your precision. You now have the ability, though, to deal with a larger class of problems expressed naturally using language, as opposed to having to encode it all. My analysts who are proficient at language and understanding the world in a complicated way, they're not going to go write Python code for something. And at what level would they write that code? It makes no sense. They're going to operate the level of language. So for them, I've got new tools now that we can use to help them do their task, but there are these biases that you have to overcome. Okay, let me quickly skip over all this. So that's the language model. Turns out you can compress essentially all of computing into this. All of computing into, give me an input prompt, the LLM will generate the output, the result, everything. So you can look at my larger slides for KGC to see further examples of what everything means, including stuff like sorting. Input is a bunch of numbers and a piece of text that says, please sort these numbers. And the output turns out GPT-4 can sort up to, I forget exactly, hundreds of numbers correctly, more often than not, like 95% accuracy. Never trained to do that. It was trained on what we just described. This stuff, more or less. There are a few other techniques. Okay? It learned sorting. This is the big deal that is going on now. We are no longer figuring out what the system should be able to do and then pouring our knowledge into making it do it. We are letting it figure out what needs to happen from the regularity of the data that it is seeing. And maybe it has seen a whole bunch of examples about sorting. And the big thing it has, this transformer stuff has, is this attention mechanism, which enables it to build these complex hierarchical patterns, figure out that they are applicable in this setting, apply them, get results. So, and then I already mentioned scale. That is by far, I would credit the team at Google and then OpenAI for having realized that scale is what they need to go with. GPT-2 results came out. They were very interesting. And then GPT-3, they went from something like 760 million to, no, it was less than 1 billion parameters, if I'm remembering correctly, GPT-2 to GPT-3 with 175 billion. They just made this massive jump, huge scientific risk, and they got amazing results. All right, so now what do we have? We have this new computer. Let's just call it GPT-4. It turns out that actually some of the really exciting stuff going on now with Gemini 1.5 Pro from Google. One thing I should have quickly introduced to you is that in this transformer architecture, I said you're going to do this, you're going to take your input, and you're going to do a crosswise thing. Well, guess what? There's a problem here. And the problem is that this input cannot be huge, because then this crosswise thing gets to be huge, and you don't have the ability to do all of that computation. So a lot of research has gone into how do we actually represent, and also when you are doing this crosswise thing, in some sense, natively, you've lost the sense of position. There's no position there anymore. You have to reintroduce position. So you have to reintroduce some technique for saying this token is after that token. Why does that matter? Because you want to produce something at the end that depends only on the things before it and cannot look at things after. So fundamentally, for natural language understanding, you want position expressed. So this becomes a big conceptual problem. How do you express position in such a way that actually things will scale? And what there's been, again, tremendous work in this in the last few years. Google has come out with 2 million tokens. I mean, we started out with 4,000 tokens is what we could work with. The stuff that I did at Goldman Sachs for this problem, I believe my window size was 4K. I had to express all my data and all my problems in 4,000 tokens. Yes, please.
So I've read some research on the concept of overfitting as it comes to LLMs and these trillions of parameters. There's some paper that talks about the volume of data and the ideal number of parameters. In traditional machine learning, right, we have the concept of overfitting and how you assess that. In LLMs, how are you able to assess basically, whether to adopt this result and what are the dangers of it?
Yes. So I should probably just take this because I think time, please. How much? 5 minutes. Interesting. No way I can coerce you into more. Okay, all right, let me just take this question. So here's the deal. What am I going to do? This progress, lots of progress. Let me take a minute and build up, and I'll come and answer your question. This is an example of how you now work with this new computer. It's taken from the MedPrompt paper. I heartily recommend that paper. This is the new program, the new way in which you program. You're telling the system, this is what I want to do. Here's the data. And in fact, you're giving it in natural language, very precise instructions. I want Y1 and Y2. Two things, I've got my data X, Y1, Y2, Y3, Y4. I want these things, Y1 and Y2, to be in the same plot. Y3 is in another plot. Next to that plot, I'm describing the output layout in language. How incredible is this? That's taken by GPT-4. It produces the stuff that you see. Okay? That's where we are. As professional programmers, we're trying to figure out how we can reliably ship products on a computer that's able to do this and still make all sorts of embarrassing mistakes. Right? So this is what the new programming framework looks like. And now I come to, so in fact, let me come to this, confessions. Right? So the short answer to your question is this. Actually, programming today is a big bear, meaning it's a huge problem. You can write, essentially the discipline of software methodology, software programming has not yet been developed appropriately for this new space. You can write the complex programs that I gave you, that I showed you, and what will happen is, if things are working, they work beautifully. But there's something you wrote that it didn't actually follow. And you don't get that answer. So in the KGC talk, we talked at length about this. We had a program, we wrote inputs to figure out a tour through New York City that must go to restaurants, must go to museums, blah, blah, blah. So you're solving a combinatorially complex problem using an LLM by giving the English text as input. Turns out it does most of it right. But there are a few constraints that were maybe too complicated for it. It just ignored. And now I have no way to debug this darn system. Because what am I going to do? The big problem here is that the GPT-4 class machines are old computer that we had. I could look at its internal memory and see what's going on. I wrote the code that had the agency that moved those variables from here to here. So I have a whole debugging framework that I can use to figure out something wrong in my instruction. Here's what I fixed, because I can look at all these innards. GPT-4, there are no innards to look at. It's a black box. So I am now debugging a really complicated application for my analysts by writing a bunch of language which it chooses to willfully ignore whenever it wants to. How am I going to get professional code out of this? So this is a big problem. Now, it turns out that obviously everyone doing deep learning and large language models is very concerned about this problem. Yesterday, so this is how amazing this world is. Yesterday, a wonderful set of papers, again, they've been working on this for a while, from Anthropic, came out where they are finally able to expose in a large language model, in this case Sonnet, which is one of their premier GPT 3.5 class models, they're actually able to identify features. So finally, we are able to see that in these massive collection of neurons that you got, when you send this input, things, some of them get activated, others don't, and that results in the output coming here and you get your result. Finally, we have two tools now, these sparse autoencoders, which you can use to find patterns in those activations and tie those patterns to features, meaning things that you and I as humans would say make sense in the world. There is a place in the world called New York. So if I am to give this system a piece of text that references New York or an image that references New York, I would expect the pattern for the feature New York to be activated. And we all thought that this is going on inside, but there's no way of getting at it. Now with these papers, they've released millions of patterns that they have identified in Sonnet. So you finally have a tool where this black box is being opened up for programmers like me to say, fantastic, not only can I recognize New York got activated on this, that's great, I intended it to be, so I'm on the right path with the program that I'm giving in, but also you can manipulate the result. Just as I could when I'm writing code in the old style. By changing my code a bit, I can now manipulate the result by saying this set of activations, clamp them high, because I want to operate in the New York context and nothing else. So again, it's like doing surgery with an axe. It is quite brutal and very sort of, but at least we got something. Before this, we didn't even have that. So now finally we have some ability. This is just coming out, though this work has been going on for several years. It's reverse engineering. It's trying to figure out how these things work in a way that can be explained by humans and used by them to get causally better results. So we've got much better results. That's what I've got here at the bottom that are just coming out. I expect this is going to continue. From a math point of view, this looks right. The way that they are doing it looks completely right. But these are the problems. First of all, I should make it very clear there are a whole bunch of problems that this technology is really, really good at and don't have an issue. I want to summarize certain things. Even from a certain point of view, I want to extract facts like what I explained to you about doing things with loan documents. I don't have a problem. I can teach some of the programmers in my team what are the techniques to use to do it, and I'll be quite confident they will come out with something that I'll put a bunch of code around. It will work. I can ship it in production. The problem is this technology lends itself to us imagining far more complicated things. How about extracting headwinds and tailwinds? Every financial analyst has a way of looking at a particular stock, which is operating in the real world in a particular context, and say, here are headwinds that are going to hold this back, here are tailwinds that are going to propel it forward. These are essentially complicated concepts that the financial analyst community has figured out over a period of time. They write small pieces of text to explain these things, and now we are looking at a GPT-4 trained on internet data, knowing nothing about finance. We are looking to get it to produce headwinds, tailwinds out of analyst text that we provide to it. That is what leads you to, it's hard to identify zones of stability. You want to analyze, Fed speech. The Fed governors are giving some speeches. You want to analyze the content to figure out, is this bullish on inflation or whatever, interest rate tightening, whatever. Whole bunch of features you can define. You can get GPT-4 to generate numbers for those features. How stable are they? If the guy said a few words differently, would the numbers change significantly? Well, in some cases, you want those numbers to change significantly if a few keywords got changed. But most of the text is not like that, so you want to be smooth. Now you need to figure out what are the zones of stability for your code so that when you ship it in production and it meets new text coming in, you can still tell your analysts, trust me, it will work. Very hard to get to these concepts today. All right, so I think I should stop because I am over my 5 minutes. So let me just say that I think now with some work that we have done, others are doing, we are able to use LLMs to do a better job of working with LLMs, if that makes any sense. So GPT-4 class machines have this ability to recognize, we give it a problem, we say produce an answer, it produces an answer. Now we give it another problem, we say, hey, I gave you this problem and you produce this answer. Is it correct? How stupid. But yes, it actually can see errors in what it produced, and then you say, and then please fix it. So you go around this iterative self-fixing loop. It actually works in some cases for GPT-4-like architectures, not GPT-3. Okay? You can also ask, okay, I've got this problem. Please develop a plan that can be used by another LLM to execute this problem, and so on and so forth. So all of these, what we used to call meta-programming idioms, are now accessible to us because ultimately they're all expressed in language. And this is the Uber language processing tool. I don't mean that Uber. Language processing tool. So we have this ability to build towers of reflection and fold them back into the same thing. I don't know if that made sense. That's using a lot of programming languages terminology in there. Turns out, my old school, Carnegie Mellon, these two guys that you see back there, they're both no longer with us, Alan Newell and Herb Simon, developed some ideas that are very prescient. Their system called GPS, General Problem Solver. Those ideas are coming back into play now because we finally have the system that can actually work with language. So I am going to stop here, and apologies for taking up too much time. But this last thing says, for those of you, there are a bunch of colleagues in my area who I'll call my dear AI bros, who are of the point of view that we are in a world, they're going to get extinct because the super AI, AGI will overtake the world, etc. Well, my view is we start, I call it the AI clock. When we hit midnight, we start from the noon. When we hit midnight, the world will end because AGI has taken over. We are at 15 minutes past noon. It's a long ways to go. Thank you so much.